But I want to start with a theorem of Mahold. And that is that if P is 0 in an E infinity ring, R, and R is algebra plane. And I promise in my abstract that my talk was actually mainly going to be algebra. So most of the time when I say these things, just imagine that I'm only saying things about algebra. And a lot of statements will be true. Namely, if P is 0 in an ordinary ring, then it is in fact an ordinary ring. So that's the algebra statement of this is still true, but I get a topological enrichment of it as well. Where's the P coming from? I don't know. Like,
what does P has to do with infinity R?
Oh, so
characteristic.
It can be in this case. So when I look at pi 0 of my ring, that's just an ordinary of my infinity ring. That's an ordinary commutative ring, and it's the characteristic. Basically, it's just a statement of if P is 0 in that ring. Yeah. So yeah. All right. So this theorem is generalized greatly by Jeremy Hahn. Where he showed that actually I could think of this as being a statement about rational homology or rational homogeneity, that HQ localization vanishing. And then it can be a statement that if I look at any of the Morava K theories, Kn star of R is 0, and R is E infinity, then Kn plus 1 star R vanishes. So if you're thinking from the finite perspective, this is kind of the exact opposite of what you would expect. There we know from work, I guess going back to, I learned this from Ravenel, that if I have the K-nth Morava K theory vanishing, that actually tells me something about the earlier Morava K theories vanishing in the finite case. And in fact, if n is sufficiently big for anything finite, then the Morava K theories are basically the base change of the mod P homology. So unless the mod P homology vanish, those don't vanish. So in some sense, this is like diametrically opposed to that, in the sense that being 0 to the left is different than being 0 to the right. And here we're seeing both cases. We'll see that equivariantly, even more structure or even more constraints are placed on this by some of the structure. So for equivariant cases, we get a lot of choices. So we have choices for what replaces E infinity. And I'm going to now go on a fairly lengthy aside to motivate this.
In your comment with the Ravenel thing, the point is that R here, of course, most of the time is not finite, right? So that's
yeah,
that's
exactly. Yeah, thank you. Thank you. That's a great point. That it's really telling me that if I'm finite and E infinity, then I better have been detected in rational homotopy. So thank you. All right. So here's I'm calling this an aside, but it's going to be like, I don't know, half the talk. So let's just think in spaces. So given a space X, we get automatically a functor that goes from the category of finite sets and isomorphisms into off. And this is going to just take a finite set, T to maps from T into X. And in fact, I'm just using the isomorphisms. This automatically extends, so I really have finite sets op going into top. And I use the fact that finite sets iso sits inside both finite sets and finite sets op. And so the Siegel model of what does it mean to be commutative is that a commutative monoid structure on X is the same data as an extension of this functor over all of finite sets. And why is this the same data? Well, I just have to check what happens to a couple of maps of finite sets that I like. So if I look at point, disjoint union point, goes to point, well, this gives me a map X cross X, which is isomorphic to maps from the 2-point set into X. I use my extension, which takes me down to maps from 1 point into X. And that's X. And so here's my multiplication on the X. And if I look at the twist map on this, well, this diagram commuted, so that gave me a corresponding commutative diagram. Which showed me that my multiplication was commutative, and you can check with one other diagram, empty set goes to X, or goes to point. This gives me my unit. And so I have the same data that I normally would, I've just packaged it in a different way. And if you're familiar from sort of the higher categorical approach, this is basically the way that Lurie ends up talking about commutative monoids and E infinity monoids. He's using finite pointed sets. I'm going to ignore that distinction here. But these are the interesting maps that one looks at in this data, these ones that look like, fold points together, or take the empty set to a fold. Okay, while I'm erasing, any questions? Yeah. Is that about having music that I played during this? But then I thought, oh wait, I think these are recorded, in which case then there's copyright issues. And then I thought, oh, these are recorded, in which case there are copyright issues.
You just sing, right? Then you control the copyright.
None of us want that. But if you wanted to, Jesper.
Thank you. Just have to find my tune.
I'm creating space for you. So I want to do the same thing now equivariantly, and I can start to see the sorts of things that are going to change. So first off, well, all my g's are always finite. So I'm going to let in G be finite G sets. And in this case, I actually have a lot of categories that sit in, oops, I was ISO. A lot of categories of interest that sit between fin G and fin G ISO. The things that I would want for this are things like point disunion point goes to point. Well, I'm going to want that sort of behavior. Empty set goes to point, I'm going to want. But then the additional data here, the additional data was that I had sort of a single interesting object, namely point. And then I formed the finite coproduct closure of that, the finite coproduct completion of the category that was one object and only the identity. And that gave me this. Well, it really gave me this one, and then I was taking isomorphisms in it. So I can talk about other various kinds of finite coproduct complete things. So I'm going to say that an indexing subcategory fin G is a wide subcategory. Right, is fin G of such that is pullback stable and finite coproduct complete. So what do each of these words mean? Wide here means contains all of the objects. Category theory sometimes call this luff because that's full spelled backwards. No, really. That's both a true statement and the reason. I'm going to call it wide for obvious reasons. Pullback stable means that if I have a diagram, and this is in my category, and then I pull back along an arbitrary map in the base, then this map is also in my category. And finite coproduct complete means, well, it's closed under coproducts. And so I see anytime I have an element, I have, say, the coproduct of all my maps, and then I also have fold maps. So what does this give us? Well, I can ask for the same kind of structure for any one of these. So, I don't know.
Can I just check? So is this like strictly more general than having a family?
Pardon me?
If you have a family, then you definitely have something like this, right? Like if you have a family of subgroups, closed under subconjugations and so on.
A family of subgroups tends to not give me all of the objects. That's a great question that I'll talk about happily afterwards.
Right, sorry, wide, okay.
Yeah, the wide tells me that my family of subgroups has to be all. But there is a really interesting story in the family case.
Could you quickly repeat what finite coproduct complete means? Because if all objects are in there, I'm not sure what I understand.
So it's really a statement about maps, is the whole thing. And what this is telling me is that I have the fold maps are in there for every object. And this map is in there for every object. And if I have S to T and S prime to T prime, then I can coproduct these together.
And the maps that appear when you build the coproduct are in there or something.
Yeah. So it is a statement about, like, what are the kinds of maps that show up. So if I just had isomorphisms, that's not finite coproduct complete, because I'm missing things like the fold maps, the inclusions of the summands. But then, equivalent, I can think about this as it's symmetric monoid. It's a symmetric monoidal subcategory for the coproduct, and it's closed under the fold maps. And that's another way to think about it.
But this, once you trace through, it is just a categorical notion of finite coproduct.
Pardon?
I mean, this translates into a categorical notion, or you're just spelling out what?
I was just spelling it.
Okay, yeah. I mean,
The category has all objects, so it's
right,
not
but
being closed on the coproduct. That's not
it's not being closed under.
for the object because we have.
Yeah. But
something.
there's not. Okay, so you are really making a definition. You cannot trace it into just some universal property, unless this is a universal property.
It's a property of a wide subcategory to be
Yeah.
symmetric monoidal, where the inclusion is symmetric monoidal. It's a property.
I can view this as sitting inside all finite G sets, which is finite coproduct complete.
Yes.
And I can ask, is this a finite coproduct complete subcategory of that? So in other words, if I have some collection of objects, do I have the fold maps? Do I have the inclusions of summands? Is it closed under taking coproduct?
I mean, I guess what Jesper's saying, right? I mean, this is saying that the coproducts have the coproduct property relative to the subcategory, right?
Yes, thank you. Yes. Yeah. Yes. Okay. So I'm going to say an O commutative monoid is a G space X plus the data of an extension. First we'll say compatible extension from fin G iso to top G. And I want to extend this over fin G O. And then I said compatible, so spell that out briefly. I want to avoid erasing so much. So compatible here is using I guess it was here and erased. It's using the fact that fin G iso also sat inside fin G op. So I had fin G iso. This was inside fin G op. And it sat inside fin O. And here, it's sitting inside, this is, functors out of this, well, I had the natural extension for anything of a functor out of this given by just maps out of it. That was the restricted Yoneda lemma. And then here, I had my extension, and so I can ask for compatibility of these two maps. And this is essentially the universal property of the span pattern. Oh gosh, I should have been erasing while talking about coproducts.
And I couldn't sing my song, right?
Oh, right. Oh, so you're ready. Okay, I'm happy to introduce Jesper. While I'm erasing, he's going to be singing a song for us.
There's a lot of pressure here.
I believe in you, Jesper.
Yeah, that's good. That's good, Mike. At least someone does.
We need to know what O stands for. Is it O equal?
Pardon?
What does O stand for? No O.
Yeah. It's actually sort of secretly coming from operad, but so no, not orbit, sadly. So I can build a category. Ooh, this is not dry. Let AO be the category with objects finite G sets. And the morphisms from S to T are going to be isomorphism classes of correspondences. And then the condition that results in the adornment O here is that the forward map is going to be in my fin G O. And this has products. This has all the properties. Have you ever seen the Lindener category? It has all the same properties of this. So I can talk about Mackey functors, and that's what I really mean here. So compatible extension. Means that I have a map in G. Sitting inside this as the wrong way map. And this one over to top G. And on objects, remember this was just specified by T went to the space of maps from T into X. So if I spell that out a little more, well, it takes disjoint union to the Cartesian product that I know just from what's happening over here. And so I get, for every orbit, I have map from two copies of G mod H. X. Well, this is the same thing as the Cartesian square of the space of H equivariant maps from G into X. And then this went down to maps from G mod H into X, which again is the space of H equivariant maps from G into X. So I have not only a multiplication, I got this from my extension. That was because my indexing subcategory was closed under these fold maps. The existence of the fold maps gave me a multiplication on the G mod H level for everything. Then I also have more. If I have G mod H, let's go to say a point. Then this gave me a map from H equivariant maps down to maps from a point into X, so that was X. So putting it all together, this data says I have a bunch of commutative monoids. So one for each classic subgroup, so for all G mod H. And this one says I have transfer maps. Taking me from the H equivariant data at X, because this space, H equivariant maps from G into X, as a G space, this is entirely determined by the H equivariant structure of X. And so I have this map that took me from something that cared only about X as an H space back to X as a G space. And this is a map of commutative monoids. You write down the sort of corresponding diagram with G mod H, disjoint union G mod H goes to G mod H, or goes to point, disjoint union point. and ends at 1.
Can I ask a question?
Please do.
So your definition of this span category, you take isomorphism classes of spans and not like the 2 category of spans.
Yeah, yeah.
So how are you not ending up with like an HZ module then?
So, yeah, here I basically am. And so this is the sweeping of the rug. If I really wanted to do this non-algebraically, then I would actually work in something like Barwick's infinity 2 category of spans, where instead of taking the ISO class of correspondences, even not working in the 2 category, I want to record the higher coherences. And then I actually get the right notion, because you're right, these give me exactly like points that commutative model is, and those are algebra things. If I want something that's the E infinity version instead, that's the thing. Any other questions?
For the transfer maps,
Yeah.
should they be landing in G equivariant maps from point to X, which would be the G fixed?
So it's not, so it's that this was really maps from G mod H into X. And so that would be, if I did the same thing for a point as G mod G, that's G equivariant maps from G into X. And that's just X again, so I could write it that way, but I'm not actually gaining or losing information. Okay, so this was sort of that additive warm-up. And now I want to do the more multiplicative one to get me back to the same kind of things that I'd led with. And so what I want to do is I want to play the same game, but with tensor induction instead. So play with tensor induction. But here I needed this to sort of set the framework, because if you notice, basically as Tom pointed out, I'm just producing Mackey functors. But I'm producing Mackey functors that only have transfers parameterized by my O. And in fact, the data of O that I gave was exactly the conditions that you need to know that some collection of things in the linear category formed a subcategory. What exactly did I want for having just some transfers? If you unpack it, it was the definition of an indexing subcategory. Turns out that's the same thing that I can do to parameterize the multiplicative version. And so now I'll do tensor induction, but I can sort of think of this several ways. I can do this topologically, or I can do this in Mackey functors. So I'll have sort of 2 parallel threads. So first, in Mackey functors, so in algebra, we have strong symmetric monoidal functors which I'll write as the norm from K to H. And this goes from K Mackey functors to H Mackey functors. And these have the property, here's actually how you would compute any of these, that commute with sifted colimits. And if you take a representable, is A of K mod J, this goes to a representable. So if you want something to think about instead of the rest of what I talk about, then you can use these two properties to actually compute a bunch of the norms of various Mackey functors in a bunch of contexts. So here my A here is, this is a O for the O corresponding to all of phin G itself. So I have everything inside of phin G. So this has all the transfers. And what's the topological statement? So in topology, we have strong symmetric monoidal functors. Which I'll also write the norm from K to H, from K spectra to H spectra. And these have the properties that they commute with cyclic colimits. And if I take the norm of a suspension spectrum, then I get the suspension spectrum of co-inducing up. Oops, okay. And so now I can, in either of these contexts, play the same game and ask for extensions. So, and ask for the same kind of O commutative monoids here. And so in this case, I'm just going to ask now for an extension of phin G iso into, maybe I'll just do Mackey functors over phin G O. But now my map is different. My map here took T, and I'll say my map took G mod H, it'll be easier to describe, to the norm of the restriction of M for my fixed object M. And so the prototypical example is actually coming from spectra. So as a sub aside, and then I'll actually leave both the sub and the main one. These functors, this is left adjoint to the restriction on comm in G spectra. So if I look at actually commutative monoids in the category of G spectra, then this norm, this tensor induction, is left adjoint to the forgetful functor. Again, these are kind of things that, like, it may seem kind of weird when you think about it, especially if you've never thought about tensor induction. But if I think about it as like induction works really great, as in it's the left adjoint to the forgetful functor, if I'm using the categorical coproduct, and then I just categorical coproduct cardinality G mod H copies, and I permute them in the expected way. That works in in spaces where I took the disjoint union, that's what I normally get. It works in vector spaces where I took the direct sum, that's what I normally get. And for commutative monoids, the tensor product is the coproduct. And so tensor induction is the left adjoint to the Bigotto function there. And so because I have this adjunction, this gives me, for any commutative monoid, maps of commutative monoids. It's just the co-unit of the adjunction. Okay. So in algebra, these kind of objects have a different name, and they've been studied pretty extensively. In algebra, these O commutative monoids are Tambara functors, or incomplete Tambara functors, introduced by Tambara to study sort of the interaction between a multiplicative transfer and an additive transfer in things like group cohomology. And Tambara called these TNR functors for transfer, norm, and then restrict. So, I can go pretty far, but I'll say it more heuristically. So, a polynomial is a diagram of S, U, V, T. And I can have a category which I'll call P, with P of ST is going to be isomorphism classes of these. So I'm using the language that often category theorists use. In homology theory, we also follow Strickland and often call these bispans. But I want to think of these as polynomials because this map says these are my variables that I'm starting with. And then I want to think of U as saying how many ways am I going to maybe duplicate any given variable. And then I'm going to take some collection of those variables and multiply them. And then I'm going to add up the whole resulting concept. So this is the sense in which this kind of thing does generalize the notion of a polynomial, especially if I were to describe what the composition of these is. And I want to finish close to on time, so I'm not going to say anything about the composition of these. But if you literally write down what's the distributive law for multiplying polynomials, like that we learn, I don't know, in the US we learned it in probably middle school, which means here it was probably elementary school. While you're walking through the streets following a man on horseback wearing armor, I've learned a lot about the local culture here. And then this is giving me just this categorification of the notion of a polynomial. And so a Tambara functor is a functor from P into set such that it takes disjoint unions to the product. I should probably call this a semi-Tambara functor because it's not necessarily group-like, so I'm getting semi-rings instead of actual rings. But one of Tambara's big results when he introduced these is that I can group complete such a thing with impunity. And I recommend Strickland's monograph for learning more about these. So this is the notion that I got, and that's a theorem due to Rolf Hoyer and Christian Mazur. And that is that Tambara functors are the same thing as G commutative monoids. By which I mean O commutative monoids for the O such that thin G is thin G. So that terminal. Now I want to start tying this back to what we had before. So now let's look in the topological case and think about what this sort of thing means for the spectrum.
Excuse me. Should that finish G commutative monoids in Mackie?
Yes, thank you. Yeah. Okay. So if I look at the Balmer spectrum of G spectrum, then this was worked out by Balmer, and they showed that I can recover this out of a bunch of copies of the Balmer spectrum of just spectra. And I'm going to take a copy for each conjugate class of subgroups. And the map, this is like a bijection on points, and the map here is, you basically just consider spec of the strong symmetric monoidal maps given by the H geometric fixed points. But if you're not as familiar with the equivariant commutativity side, the geometric fixed points are probably what you'd be thinking of if you were just to guess what fixed points are. They follow the same kind of behavior that the fixed points on actual spaces do. And they commute with suspension spectra. That sort of tells you how to actually compute the geometric fixed points of anything. They're strong symmetric monoidal, so I can use them, whereas the categorical fixed points aren't. In algebra, I like to think about this as the map that just kills off the transfers to H and then take H fixed points. So put another way, the failure of the fixed points to be strong symmetric monoidal is the fact that I have this transfer that comes up that's not a multiplicative map, it's just additive. And that sort of screws up the H fixed points doing the right thing, because I have to sort of put in the transfers. If there were no transfers, like in spaces, then the fixed points are strong monoidal. And the geometric fixed points sort of does this. I can do this in algebra, but the other thing that this tells me, that the transfers are also the failure of things like these multiplicative maps to be additive in some sense. So let's apply phi h to the norm from H to G, phi h upper star R, back to R, and this gives me, phi g, excuse me, that's important, phi g, to this, and I get, well, phi g of the norm goes back to phi g of R And this is the H geometric fixed points of R via it's a diagonal, which isn't a map of spectra because I have the issue of transfer terms. But once I've killed off the transfer, then the diagonal is a perfectly well-defined map. And I get a map of just ordinary commutative ring spectra from the H geometric fixed points of R to the G geometric fixed points of R. So if you think about what this means for, say, that tells me something about if I have vanishing of Morava K-theories on subgroups, then that forces the vanishing of Morava K-theories on bigger groups. So what I want to end with is just the rational story, because this is a really beautiful one. I like due to Christian Wimmer. And while I'm slowly erasing, any questions?
So you're saying that the support of an infinity ring in the spectra would also be open.
Yeah.
That would be not equivalently.
Yeah, yeah. All right, so now I want to apply this rationally. And I get this theorem of Wimmer. And that is that when I take the map that goes from rational equivariant commutative rings to just functors from, let's say, product preserving functors from fin G into ordinary rational commutative rings. And since I'm rational, these are the same thing as infinity things, as commutative TGAs. There's lots of nice models for this. And the map here takes R to G mod H, goes to the H geometric fixed points of R. And this is an equivalence. So the surprising part is actually the covariant behavior, and that was the map that I wrote there. So if I look at this for G is CP, I'll just expand this a little. I have two pieces of data. I have a value at CP mod E, and this has an action of the endomorphisms of CP mod E, well that's CP, and I have a value at a point, and I have a map between these. So this is the whole data. On the other hand, I could have interpolated between these. So I could have taken just E infinity monoids, so no norm maps. And these are functors from the isos in the orbit category into com. And the orbit category with isos or coproduct complete to get, close up under coproducts, not coproduct complete, close up under coproducts to get, to get the finite G sets and isos. So I had a forgetful functor that went from here to here. And that produced diagrams where I'm ignoring this map. And so this is a kind of forgetful functor. that throws away the norm maps. Now, in both cases, and this is what I want to end with, I can talk about trying to classify deformations of these. I can try to talk about infinitesimal deformations and do a cotangent complex and try to ask, what does it mean to be, say, etale? Or what would it mean for a map to be? What's the vanishing, the cotangent complex? And so from the setup, I'm sort of giving a suggestion. First, I could just everywhere take omega 1, or take the cotangent complex everywhere. And that gives me a kind of module over this. But Strickland showed that's not an equivalence of categories. I have to do things like also control this norm map. And even if I do that, I get a surprising result. And this is the last thing I'll say. This is work with B and Tyler Lawson and Dylan Wilson. And that is that that the vanishing of the E infinity cotangent complex is equivalent to the vanishing of the G infinity, or equivalently com G cotangent complex. Or in fact, anything that sits between them. So even though the cotangent complexes are going to be really different, they're built out of sort of different omega 1s, the vanishing of them is the same. And so why is this? Let me just take a breath and not write anything to say it. If I had some map and omega 1 vanished on each of these pieces, well, how do I get the omega 1 for the left-hand side versus the one for the right-hand side? I quotient out by the images of those norm maps. But on the other hand, if I look here, there were no norm maps that landed here. So if it vanished here, there's no difference between vanishing here and vanishing here, because I didn't have any norm maps that I had to quotient by. The next step, I had something that was a quotient of what was here by the image of the norm, and I end up writing down some sequence where I have all of the terms are 0, and so I get to deduce that all the terms are 0. And I'm out of time, but I can say more about it.